Today we're going to look at Newton's law of cooling. This is an application for differential equations, so it's not really anything new as far as this unit's concerned, but it is a new way to apply what we've learned. So here's the idea behind Newton's law of cooling. If you think about putting an object at room temperature inside of an oven, if the oven is 300 degrees versus putting the object in the oven when the oven is 400 degrees, when the oven is 400 degrees, the object is going to warm up more quickly than when you put it in an oven that's 300 degrees. And the reason for that actually doesn't have so much to do with the fact that the 400 degrees is hotter as it does the fact that the difference between the two temperatures is greater. So let me explain what I mean by that. If you had an object that was already 100 degrees and you put it in a 300 degree oven, it would warm at the same speed, theoretically, as an object that's 50 degrees being put in an oven that's 250 degrees, because both of them have a difference of 200 degrees. So that's my point with saying it's really the difference between the two temperatures that matters, not simply the temperature of the surroundings. And this is actually called Newton's law of cooling. It's usually used to talk about how objects cool, but it works just as well for objects that are being heated up. So the equation you can see right here, y prime equals k times y minus ts. Okay, so y represents the temperature of the object that's going to be changing its temperature. So the change in temperature is directly proportional to the difference between the temperature of the object and Ts, which is the temperature of the surroundings. So the greater that difference, the faster it's going to change. So that also means that as the change gets smaller and smaller, as the objects become more similar in temperature, the speed at which the object is changing is also going to be less. So we know how to solve differential equations, so that's the first thing we need to do. We change y prime to dy over dt. We're going to be talking about time, so lowercase t will be time, uppercase T will be temperature. Now we need to multiply both sides by t. And this is a subscript s, just so you know. It's not t times s, it's t with a little s, just to denote that we're talking about the temperature of the surroundings. Now I need to divide both sides by y minus ts. I cannot separate that, so I have to take the whole thing over to this side. So that's all the separating that needs to happen. We have the y's on the left, and we have all the t's on the right. So we take the antiderivative of both sides. We integrate both sides. Okay, dy over y minus ts is of the form du over u, so it'll turn into the natural log of y minus ts. And the antiderivative of k, keep in mind k is a constant, so it's just like having a 3 there or a 4 there, will be kt plus c. So our last step is to simplify. We need to solve for y. We get e raised to both sides, so it becomes y minus ts equals, this c comes down front, so we get ce to the kt, and our last step is just to add ts to both sides. So from now on, instead of starting with the differential equation like we did up top that I'd circled earlier, you can just start with this equation. You can start with y equals ce to the kt plus ts. So you notice it's not that much different from the one we were using before, the basic y equals ce to the kt. Again, let's just talk about what each of these things mean. Y represents the temperature of the object. Little t represents the time. K is a constant that's going to represent the rate at which it's changing, temperature. And then Ts is the temperature of the surroundings, which for our purposes will remain constant. That may not always happen in the real world, but that's what we're going to go with, and we won't worry about that. But C is a little different. Normally C is the initial amount, so normally we would think C would be the initial temperature of the object, but it's actually not. It's actually the initial difference between the temperature of the object and the temperature of the surroundings, and I want to show you how that works. Let's say we put a 100-degree object in an oven, that's at time 0, and the oven is 300 degrees. Or actually, let's change that. Let's say we have a 300-degree object that just came out of the oven, coming out into a very warm house that's 100 degrees. So if we subtract 100 from both sides, we get 200 equals C. So as you can see, no pun intended, the 200 is the difference between the two temperatures. It's not the initial temperature of the object. So I'll write that down and then we'll look at examples. So for this type of equation, C is the initial difference between the temperature of the object and the temperature of the surroundings. Okay, if you'll move on to part 2, you will see some examples of this.